Well, hello, ladies and gentlemen. Mr. Dorfa here for yet another installment of Physics Video Notes. We are moving on to section 2, and as I kind of gave a disclaimer on last week, it is going to be a rather lengthy week of videos and problem banks. One of your longest ones you're going to have all year long. Because today, which is Monday, tomorrow, Wednesday, Thursday, you're all going to have a very short discussion over new formulas and homework. However, I am going to try to mix things up a little bit and not have any of the homework or the problem banks, I should say, due until Thursday evening. So be paying attention to the due dates for all of these problem banks that you're going to be assigned, okay? But let's take a look at what we're covering today, and that is acceleration. Okay, this is not a new term to you. You talked about this in intro to Chem Phys. So again, this video going to be a somewhat short one. We're going to do a couple problems together, or you can follow along with me if you so choose. But we're going to talk about acceleration today, and you're going to have an addition to your formula sheet, and that's going to be the formula for acceleration. And I've got a table that you'll want to take a look at. It's actually table 3 in section 2. And then tomorrow we'll continue on working with the different formulas that we can encounter. All right, so throughout this section, here are the objectives. Describe motion in terms of changing velocity. Again, not a new term. Compare graphical representations of accelerated and non-accelerated motions. That's an interesting thing we're going to cover today. And apply kinematic equations to calculate distance, time, velocity under conditions of constant acceleration. Right there. That little statement right there. Constant acceleration. Okay? That's a big deal. That's a big clue in the problems that we're going to work on that we need to make sure we pay attention to. Most of them will say constant acceleration or it's understood, okay? So let's begin our discussion. So what is acceleration? Simply the rate at which velocity changes over time. Okay, we have very recently discussed the differences between speed and velocity. The main one being direction, okay? Because acceleration utilizes velocity, that means it has both a magnitude and a direction. As I was kind of going over some of your 2.1 quizzes, I made notes on some of the problems that said, do not forget to include direction when possible, okay? And acceleration isn't only about whether or not its velocity changes, okay? Or if they break it down as speed or direction, because speed and direction are velocity in a sense. But if either speed or direction, which again equates velocity, or both change, the acceleration then changes, okay? Even if we have a car that is going around a track. They used to have these car races where you put a little model car on a string around a pole. These cars would zip around these poles going at high rates of speed, but their speed was always pretty much the same. But they were constantly changing direction going around that circle. They're not going just in a straight line, they're going in a circle. So they're constantly accelerating. Even though the speed is remaining the same, their direction is being altered. So those are some things we have to consider when we're talking about acceleration. So how do we solve acceleration? Where you see the formula right here, okay, where we have the average acceleration. Now, again, we use average because throughout the time that an object is in motion, it's not going to always be the same. So what we do is we calculate the average. We call it the average because it might change from here and here and here. But overall, the whole distance, we have an average acceleration. Anyway, you have delta V, which again means change in, and that's divided by delta T. So we have a change in velocity divided by our change in time, or basically how long it took for this change in acceleration to occur. And to find the change in velocity, you take VF, which is the final velocity of the object's motion, minus the initial velocity of the object's motion. Okay? So again, add that to your formula sheet. That's the only one we're going to get today, but you're going to have quite a few the remainder of this week. So let's take a look at how we can utilize the acceleration formula to help us solve a certain question. So we have a shuttle bus that slows down with an average acceleration of minus 1.8 meters per second squared. How long does it take the bus to slow from 9.0 meters per second to a complete stop? All right, so I'm going to hop out of here. I'm going to go in here, and then I'm going to bring out the magic board here. All right, so again, I have to darken this smidgen. Okay, that should hopefully work. Beautiful. So again, we have acceleration is equal to VF minus VI over T. Again, since we are dealing with formulas that are going to start having more and more variables throughout this chapter, I always like to make sure that I can keep track, organize my information. Okay, so again, what do we know? Well, we know that the bus was initially had a velocity of 9.0 meters per second. We also know that the scenario in question, the bus had a final velocity of 0.0 meters per second. And we get that information from the fact that it said came to a complete stop. So our average acceleration was negative 1.8 meters per second squared. And so we're trying to figure out how long it took. Sorry, you can't see that little icon's there. How long it took for this to occur. Well, that means we have to rearrange our formula. So I need to get this t out of the denominator and isolate it. And so throughout the whole process, again, this shouldn't be anything new to you. We've done this many times, especially in intro. We're going to have t is equal to VF minus VI over t. Okay? Pardon me. So once we got it rearranged here, you might like to be the person who puts it in there and then rearranges as you go. That's fine. But I like to keep it here because it's pretty simple. There's not a lot of numbers kind of muddying up the area here. So simply just input your values. Again, our final velocity was 0.0 meters per second minus our initial, which is 9.0 meters per second, divided by the average acceleration. Oops, I made a mistake up on this one. That's supposed to be an A. You get negative 1.8 meters per second squared. So once you solve for this, you're going to find out that it takes approximately 5.0 seconds for this bus to slow down from this particular initial velocity. And it's a good thing that we had a negative value here and a negative value here, which would make it positive because time can only be positive in value. Okay, so we're going to come back after I finish talking about acceleration. We're going to come back to the practice problems that we're going to do together. Okay, so I'm going to just bring up my beautiful face here, maybe. There we go. I know I'm upside down on one screen, but we'll get back into it here. All right. So let's look at how we can also examine and explain an object's acceleration. And we could do that graphically. So imagine, as the slide says, imagine that you are viewing a train. Okay. And according to your frame of reference, your train is going to the right. Okay. So when we're talking about a vector quantity, which velocity and displacement are going to the right, typically means a positive direction. Okay. So when we look at acceleration and velocity and time graphs here, we can describe the motion of the object itself, okay? Time being on the x-axis, velocity being on the y. The slope that we can calculate at any point in this would be its average acceleration. So looking at an object as it's traveling, okay? So as the train is moving to the right, the velocity in the positive direction is increasing in that instance, then the acceleration is positive, what we see here, okay? Velocity is increasing here as time goes on, acceleration would be positive. However, when we get to this point right here, where B is, we see that it levels off, it plateaus. So velocity is not increasing, it's remaining constant. So if velocity is constant, acceleration will be 0, okay? So there's no change in speed and or direction at that point. And lastly, we see the slope of the motion or the acceleration of the object sloping downwards, okay? That means the velocity is decreasing in the positive direction. Therefore, the acceleration at C would be negative, okay? So we can look at a graph and describe an object's acceleration by simply looking at velocity versus time. Now, this table is a nice handy-dandy table to kind of keep in mind when you are solving for velocity and acceleration type problems, okay? And how we relate those values to the motion of the object. Again, if both velocity and acceleration are positive, it is speeding up. If they're also both negative, it's also speeding up, okay? Because negative signs could just mean direction, okay? They could be going to the left instead of the right that time. Then you can, kind of look over the rest here just to kind of get an idea how you would describe the motion or visualize the motion of an object, okay? Now, like I said, over the next week or so, we're going to be inundated, that's a big word, with a lot of different formulas. So please make sure you are keeping your formula sheet up to date. But as I mentioned, we are going to go and do some more practice work here. And if you would like to join along, we are going to be doing the problems. Excuse me. We're going to be doing the problems from page 49, practice B. Okay. See if I can get my camera right. All right. So let's look at number 2, okay? Number 1 is very similar to what we saw in the practice one we did a few moments ago. So let's go to number 2. Number 2 says a car traveling at 7.0 meters per second accelerates uniformly, again, that's another way of saying constantly, at 2.5 meters per second squared to reach a speed of 12.0 meters per second. How long does it take for this acceleration to occur? All right, so here's a moment in the video that if you would like to pause right now and try to solve it yourself, please go ahead. Otherwise, I'm going to go ahead and continue with the video and go and begin solving this problem. All right, so let's list what we know. We know that our final velocity is going to be equal to 12.0 meters per second. We also know that our initial velocity is going to be 7.0 meters per second, and that our average acceleration is 2.5 meters per second squared. So again, we are still trying to solve for t. So using the formula we did a little bit ago, Vf minus Vi is equal to acceleration. And we can just go ahead and plug our values here. Again, Vf is 12.0 minus our Vi, 7.0 divided by 2.5. And we should get an answer of, I'll give you a few seconds to calculate that out, or you can pause the video, 2.0 seconds. Again, looking at our measured values here, 7.0 and 2.5 both have 2 sig figs. So I report my answer in 2 sig figs as well. All right, let's do another example here. Let's try to find something that will be different here. All right, let's do a little bit of a challenging one, shall we? we'll do number 4, number 5. Okay, we'll do 4 first. Actually, no, we'll skip 4, come back to it. Let's do number 5. Okay. Suppose a treadmill has an average acceleration of 4.7 times 10 to the negative third meters per second squared. How much does its speed change after 5 minutes? Okay. So we have average acceleration. That is equal to 4.7 times 10 to the negative third meters per second squared. And we have a time of 5 minutes. But again, units need to match up because we have seconds here. We have 5 minutes. Do a quick little dimensional analysis conversion here. Multiplied by 60 seconds per 1 minute. And we get a total time of 300 seconds. Yes, I know you probably did that in your head. That's fine. I just like to show all my work, which you should like to show your work as well. So let's do some math here. So again, looking at our very general formula, we get A equals delta V over delta T. Okay. We are trying to solve for delta T. Okay. So, delta V. I know my letters, I promise you. So delta V is going to equal acceleration multiplied by delta T. And so we get 4.7 times 10 to the negative third meters per second squared. Sorry, I'm moving my mouse here. Multiplied by the time of 300 seconds. And we get an answer for A of 1.4 meters per second. Okay. Now, let's stick with number 5 here. And it says, if the treadmill's initial speed is 1.7 meters per second, what will its final speed be? Okay. So again, we're still solving for, if I can keep this straight, delta V. Okay. But if we know delta V actually means VF minus VI when we break it down. So we're trying to solve for VF. And so in order to isolate it, get it by itself, we have to add VI to both sides. So we get VF is equal to A times delta T plus VI. Okay. And so we know that our acceleration, again, 4.7 meters, times 10 to the negative third meters per second squared, multiplied by 300 seconds. And then we add VI, which is 1.7 meters per second. Do the math where necessary, and you get a final velocity of 3.1 meters per second. Okay? So again, we can solve for anything that is part of these formulas. All right, last one, going back to number 4 here. Turner's treadmill runs with a velocity of negative 1.2 meters per second and speeds up at irregular intervals during a half-hour workout. After 25 minutes, the treadmill has a velocity of negative 6.5 meters per second. What is the average acceleration of the treadmill during this period? Okay. So again, average acceleration, delta V over delta T. Okay. Trying to get my camera here. Okay. So again, our acceleration is what we're finding. VI, initial velocity, is negative 1.2 meters per second. Now again, it's got a negative value because it's actually, the treadmill is traveling in the direct opposite direction that you are facing and quote unquote running or walking towards. Okay. So if you consider your direction a positive displacement, positive motion, then the acceleration of the treadmill itself would actually be going in direct opposition of you. okay? So that's why it has a negative value. VF, negative 6.5 meters per second. And time, we get 25 minutes, which again, got to have it in seconds. Do some quick conversion here, and we get 1,500 seconds. Okay? So, go ahead and put our information in here. We have our VF, which is negative 6.5 meters per second, minus our initial of negative 1.2 meters per second, and divided by 1,500 seconds. So just kind of doing the baby step method here, we'll find out that we have negative 5.3 meters per second divided by 1,500 seconds, and we get a total acceleration of negative 3.5 times 10 to the negative third meters per second squared. Again, we're looking for the average acceleration of the treadmill, and the only reason why it's negative, again, is because its motion is opposite of you in a negative direction, okay? I could also, if I wanted to, I could say 3.5 times 10 to the negative third meters per second squared backwards. You know, if I really wanted to say it, and as you see, I replaced the negative sign with a directional description. But this one isn't really 100% stated. It's just kind of understood. That's how treadmills operate. Okay. Yeah, if you want to do that, that's fine. I'm open for both styles there. All right. Anyway, that is going to wrap up the first portion of section 2 for the notes today. Okay. Let me see if I can't. There we go. All right, so again, if you need to go back and rewatch some of the problems, by all means. But again, this acceleration formula is something that you have done numerous times. I know you had probably just, for some of you, 2 years ago, 3 for others. But it's all the same. Acceleration is all the same formula, but just make sure you document the formula in your formula sheet for future use. And with that being said, you should be looking out for the problem bank that goes along with this one. Okay, it should be coming up very shortly. Until then, if you have any questions, get a hold of me. Have a good day.